Okay, any questions before we start? Okay, so today we'll talk about databases and data transformations as a way of thinking about categories, functors, and limits and colimits. But we'll actually mainly just stick with databases and databases and categories today, and then tomorrow will be functors and data transformations and stuff like that. And here's a key that you can use. I think I'll keep this board up throughout the lecture. So you can use this key. The basic idea is that database schemas are going to be categories. So if you ever hear me use the word schema, I'm talking about a database schema. It's like a category. A database instance is like what a database has in it at a certain time. That's a set value functor. And data transformations are what are called universal constructions. Ways of moving data from one schema to another while making no choices, just doing at least making no choices, doing what's called a universal construction. So I'll talk about this in a second, why I wrote deep reliable communication, talk about that soon. But just want to tell you that there's an open source tool available. I think this is the right website. I'm getting confirmation, www.categoricaldata.net. There's a GitHub page there. And lastly, an announcement that problem set 2 is now available if you want to go start working on that. So I guess for me, databases are about reliable communication, databases and data transformations. So imagine you were trying to understand what knowledge is, because or what information is. You could contemplate for a long time what information actually is. But we kind of can start by saying that it's stored in databases, or it's stored in our heads. So what is the data structure of what you know? Let's pretend you could put it in a database. I don't think you actually could. But suppose you could. Then if I have my database and there's some neurons connected in some weird way, and you have yours, they're not connected in the same way. They're more different than our retina or our fingerprint. How is it that I can get information to you and you actually receive it? How is that possible? So how is communication possible? How is it possible to have reliable communication that actually works? I don't think people really know this. But if we imagine that we have databases, then I have a database, you have a database, we've structured our information differently. I need a way of transferring my data to you. In other words, all the examples of everything I've learned, I want to communicate some of them to you. Because we all have some kind of simplified worldview. Like you can't get the world as it is, at least Kant says so. And so we simplify. And we forget lots of stuff. We make equivalences. We round off, etc. But still, I simplify the world differently than you do. I still need to find a way to get information to you. And so reliable communication would be when you have mathematical artifacts that allow you to continually send information in the same way over and over again. This is not the way it's done currently in the world of business, etc., where the way they move information from one database to another is through scripts, say Python scripts that you can't repeat later because the database changes, the person leaves the organization, etc., and they're written kind of as differently as the different numbers. Different ways of writing the same number. There's more ways of writing the same software script to send data. And so when you're trying to read someone else's software, it can be hard. Whereas if you have some kind of mathematical artifact, this just becomes 9 in some kind of really 9-y way, and that's better. So that's kind of the goal of this database point of view, or this mathematical point of view on databases, to make the whole database idea more mathematical, so that the ways we move information are mathematical artifacts. And of course, this takes place not just between two different databases, or between you and a friend, but between you and a future you. So you need to remember things. That's what you kind of think databases are for. But what you need to remember is different than what you recorded. You need to remember only one small aspect. So you want to query your old information and make something accessible to you now that you can use now. So data transformations, you shouldn't just think about sending it between people, but also from yourself to a future self. As your understanding and the way you schematize the world changes, how do you still recall things? Okay, so that's kind of the setup. The next layer of slightly less philosophical maybe, but still kind of philosophical, is I want to think about what I call data kinematics. And that is that data does two things, how it rests and how it moves. So data rests in databases. That's data doing nothing, sitting there being data. How it moves is through data transformations. And people talk about this less, but it's actually as important as movement. I mean, it's how you get the data from one place to another, how you change its form. Right? When you move, you change form and you change what's accessible. It's like right now this is accessible, but if I move over here, then something else is accessible. So you want to change what's accessible in the data. I want to see not all of it, just this part, make this part accessible to me. And so we want to understand how it rests, sits there, and how it moves. And so it rests in databases, and that's where I'll start. So what is a database? So here's an example. And I'll just start off with how you might see it. So you might see you have employees, and in your employee table, every employee has a first name, and every employee has a manager, and every employee works in some department. And departments also exist. And they have names and secretaries. So I'll put a double line for kind of what we're actually looking at. We're looking at employees here, we're looking at departments here, and I'll put single lines between the other columns. And so in your database, what I have now is called the schema. It's how you're simplifying the world. The world consists of these things, and here's how they're related. In fact, you might want to say that first name is of type string, or manager is going to be another employee, or works in is going to be a department. So that is technically, for me, part of the schema, where it's what these things mean. So employee, you could have employee 1, 2, 3. The first name of 1 is Alice, and 2 is Bob, and 3 is Carl, say. And the manager of 1 is 3, and 2 is the manager of themselves, and 3 is the manager of themselves. And 1 works in 101, and 2 works in 102, and 1 works in 3 works in 101. And these are of type department, so they land in the department table. And department 1 is sales, and department 2 is IT, and secretary of this one's 101, employee 1, and the secretary of this one's employee 2. So this secretary is of type employee. And that's a database. That's a database schema on top of the line and instance below the line. Instance means at some instant of time, this is what was known. This is what was true. But I could technically add or pretend that there's actually a table full of all strings, just to make the theory work out nicely, or to make the theory work out simply. The theory works fine when you don't consider there to be a table of strings, but then it's just, then you need to work a little harder. So in a table of strings, you have A, B, you have Al, you have sales, etc. in your table of strings, and you'd never instantiate that table. But it has no columns other than the ID column, and now everything here is what is called a foreign key. So you have these ID columns, the employee IDs, the department IDs, and I guess the string IDs. You have first name is what's called a foreign key. It points you from the table you're in, the employee table, to a foreign table. And manager takes you from the table you're in to a foreign table, employees. And that's what these are. They're the keys or the IDs in another table. So in sum, a database is a system of interlocking tables. But we can arrange all that information of this, just the schema of it. The schema, we can arrange it pretty nicely by saying what tables we have: employees, departments, and strings. And I'll write strings with an open circle instead of a closed circle because it is that weird, it's a data type. It's from our programming language, Java or whatever. It's not something we're going to get to fill in ourselves. So that's the slight technical difference between string and employees and departments. So now we have these three tables. We have that every employee works in a department. Every department has a secretary. Every employee has a manager. Every employee has a first name. And every department has a name. And now if you count, there's 3 dots, just like there's 3 tables drawn there. That's not a coincidence. There's 1, 2, 3, 4, 5 arrows, just like there are 5 non-identity columns. 1, 2, 3, 4, 5, all the non-ID columns. So those 5 and 5 are not coincidences. What's going on is that the arrows emanating from any dot here are the columns in the table over there. So there's manager, works in, and F name are the 3 columns there, just like there are the 3 arrows here. Any questions about that? Yep.
Can you show us an instance of where you have multiple arrows going between 2 nodes? It would be reasonable in the database.
Sure, I could put last name there.
Okay.
Okay, and I could also, by the way, add to this thing, this schema, a business rule or an integrity constraint that ensures that the way people enter data into this is not contrary to the way I want them to as the designer. So it'll throw a flag if I make a mistake, so that's useful. So I might know, for example, that for all D of type department, it's the case that D dot secretary, the secretary of that department, works in that department. So I can add any number of equations. The only rule for these equations is that they're all the form for all something. So for all employees, maybe the manager works in the same department as the employee works in, or something like that. That doesn't actually tend to occur, but because then you never get beyond your own department. But right. So if I start in a department, I can either follow the path around like this, or the trivial path, and I make them the same. And if you check over here, what it's saying is that if you start in department and find the secretary, 1, and see what department they work in, it's, again, 101. So 101, secretary is 1, works in 101. 102, secretary is 2, works in 102. So this satisfies those constraints. And tomorrow, and what we'll see soon, is that this is actually a presentation of a category. This is like the Hasse diagram for a category. And that a functor from this category, so that's what I meant when I said database schema equals category at the top. And that a functor from this category to the category of sets, what's called a set-valued functor. I haven't told you what a category is yet or what a functor is. In fact, I won't tell you what a functor is until tomorrow. But, or Brendan will, Tuesday. But what this will do is assign a set of employees, a set of departments, a set of strings, and a function called manager that takes every employee to an employee, a function called works in that takes every employee to a department, etc. And so a functor from there to set will exactly give me some instance of this database schema. So this guy there is an instance. In category theory, we use arrows a lot. So whenever I want to indicate something, I use a lightning bolt arrow, like something like that. Okay, those never mean anything except indicating. Any questions so far about this? Yeah.
I think you explained this already, but I missed it. Why string a circle but the other types dots?
Right. because string, I don't actually get to fill in my own version of what strings are.
Oh, I see, okay.
They're a data type that's kind of given to me. Okay, other questions? Okay, so that's data at rest, and then data in motion. We have to wait till tomorrow to really talk about, but it's basically like data transformations. So transformations. These are things like querying. You ask the database something like, for E of type employee, where this is like a SQL select from where statement, although people in programming language theory tend to, I think, prefer the for where return, at least I do. For E.employee, where the employee's F name equals Alice. Alice wants to know E.Workson. Let's say, she wants to know my dept. You could assign these column names if you want. Would be E.Workson and my secretary. Who is my secretary? It's the department I work in. Secretary of E name. I want to know the name of my department, and I want to know the secretary of my departments, and I want to know their first name. So this would return a table whose results are my dept. So it'll have like one row, and it'll say, sorry, I'm kind of off script here. ID, my dept, and my sec. And my dept is called, what's her dept? Sales. And her secretary is herself. Okay, any questions about this? So we're talking about querying. That's a way that data can move. There's all this data here, and we've changed its form. We've done a transformation of the data to make it a database here. This is also a database. It just only has one. This is a database whose that looks like this, string, my dept, and my sec. So we got data on this very small database, and we moved it from that one to this one. So there's something called querying, which people know best, but there's also something called ETL processes, which means extract, then transform, and then load into a new database. There is something called warehousing. So these are all what are called structured data transformations. Warehousing, converting, schema evolution. You want to move data. Okay. Any questions? So now let me tell you what categories are, because that's going to make all of this. Hopefully it'll clarify some things, and then it is kind of the name of the course. So, okay, so definition. A category, we'll call it C. That's not an E, that's a C, that's a calligraphic C. Consists of some things. One, it consists of a set, obc, and these are called objects. Elements of this are called objects. Objects don't mean anything. They're just objects. So if someone says a set of objects, they're not saying a set that's special, they're just saying a set. So okay, we have this category C, it's got a set obc, and then for every C1 and C2, if you have two different objects in C, a set called HOM sub C, C1, C2. And that's kind of old-fashioned terminology from the time when people thought about categories only in terms of homomorphisms. So homomorphisms of rings, homomorphisms of groups. Those are where the word hom comes from. It's often easier to drop this meaningless, fairly meaningless symbol hom and just write C, C1, C2. Yesterday we talked about a V category and the set of objects Brendan called X. And there we wrote distance, or I think it was like B, C1, C2, where there's a C now. It was a different situation where we were looking at V categories. Now we're looking at what are called set categories, or the monoidal category of sets. This gets very interlocked into itself, or kind of a friend of mine called it primordial ooze, because it's everything can kind of be used to define other things. So it's just very fluid and fluent in some sense. You can move between different parts of category theory and use them to talk about, define other parts. There is, if you want, a linear progression through this stuff, but it's actually nice to be able to move through it pretty fluidly. So, okay, so we have this set of objects. We have for every pair of objects a set of morphisms, and these are denoted if you had an element of this thing. Those are the same thing, whether you write a hom or a C. If you had an element, F, you would write F colon C1 arrow C2. And this guy is called the domain, and this guy is called the codomain. And co is a word that's taken very seriously in category theory. It always means the kind of the other one, the other side. But you'll see that as you see that. Okay, so you have a set of objects, a set of morphisms. For every object, so maybe you could think of places and all the ways of getting from one place to another. For every object C, there is a specified element called IDC in C, C, C. In other words, I can always get from where I am to where I am. And for every C1, C2, C3, a function called semicolon, fat semi, that takes C, C1, C2, takes any way of getting from C1 to C2, and any way of getting from C2 to C3, and produces their composite, which how it does it is up to the category. If you can do it differently than I can do it, then you have your own category and I have mine. There's not one specified way to compose things. But if you have a way to get from C1 to C2, and you have a way to get from C2 to C3, and you tell me you have a category, you better be able to tell me how to get from C1 to C3. I'm going to erase the previous thing I wrote, just to make it contiguous on this board. So these four pieces of information are what are called, well, there's some elements here, there's some things, objects and morphisms, and there's some structures, or some like ways that they're related. And these guys need to satisfy some properties. Satisfying, one, for A, that for all C1 and C2, if I do, if I have F and G, then I write F fat semi G. For all C1, C2, ID C1 fat semi F. Oh, and all F taking C1 to C2. ID C1 composed with F is F, and that's also F composed with ID C2. And B, basically that if you have F, G, and H, you can compose them in any order. I'm not writing the quantifiers for all C1, C2, C3, C4, etc. Blah, blah, blah. This is called associativity. This is called unitality. Identity is a unit. So, okay, so let me give you some examples. I guess I'll do that on this board. Okay. So, for example, every post set, each post set, Brendan said was a kind of category. So he mentioned sapiens mapping to Homo, and habilis mapping to Homo, and these two primates say. Okay, so here we have some kind of small pre-order where this is the Hasse diagram. What are the objects, do you think, of this pre-order as a category? If I said this is also a category, what are its objects? Any guesses? Okay, the objects are the dots in this case. So this category has 4 objects. And the morphisms, does anyone have a guess what the morphisms are? Yeah.
Just the arrows between the dots.
Okay. So if that was right, then you would need to tell me what the identity arrow from sapiens to sapiens is.
I guess it's just sort of implicit.
Okay, so it's not only the arrows, but also the implicit things for each dot. And you have to tell me how to compose this arrow with this arrow.
It would be the paths.
Right, so now we've got it. So the arrows, from the morphisms from here to here, are the paths from here to here. So why don't we, right, okay, great. Now in a post set, we make another thing, which is that there's only one way to get from one place to another. So if you had something that looks like this, I guess we would say that this composite is just, you would say that A is less than B, and B is less than C, and C is less than D, and A is less than D. There's just one kind of composite, there's just one morphism from anything to anything else, or no morphisms. Maybe that may not be clear, but I can talk about that later. Okay, so post sets are categories. Anything that's not completely clear, you can either talk about with me later, or look in the book. It's much clearer when we have time to say it clearly. Okay, so free categories. So all, so in this one, morphisms are exists a path. In this, what I'm about to say, morphisms are all paths. Instead of asking whether a path exists, like is A less than or equal to D or not, is there a path or not, I don't care about the difference. I just care about whether there is one. In free categories, you count all the paths. So in this free category here, how many morphisms are there? More than 6. It's more than 6. You may be forgetting. 8. 10. It is one of the answers I already said. So you need to include identities and you need to include compositions. So there are 10. So this is called the free square. Soon we'll talk about what's called the commutative square. But before we do that, let me say that there is categories called, we write 1 to denote this category, 2 to denote this category, 3 to denote this category, etc. So these are important categories, especially this one turns out to be important. It kind of looks like bool. We'll see it again. what are all the paths in this, what is this category representing? How many morphisms are there in this category? There are infinitely many. There's one for every natural number, the number of times you go around this loop. No times, 1 time, 2 times, etc. And so this could be called as a monoid. Yes, go ahead.
So the reason that didn't apply in that diagram was because you didn't draw the identity?
Oh, I didn't, yeah. In these Hasse diagrams, I don't draw anything that's implicitly there. For example, I don't draw long paths, and I don't draw reflexive loops.
But here, the fact that you did draw it.
Yeah, means I actually want it there. It's just notation, of course, but yeah.
Are you asking why there's not an infinite
Yeah.
number of morphisms?
Why didn't I draw?
No.
Or-
Asking why
Like, there are infinitely many paths in that graph.
Are there?
Well,
In lane more than.
or sorry, not at right, because
Not as-
there's not a self loop
Right,
in the
right.
morphism. Right.
Right. Yep.
Wait, so this is presenting a category as
Yes.
a graph? So it's not actually drawing the morphisms?
Right.
It's a way
Exactly.
to implicit-
Exactly. That's a great point. These are presentations of categories. And they're presented by graphs. And the reason they're free is because I didn't add any equations to them yet. But we could make them non-free by adding an equation. For example, we could say f, where f fat semi f equals identity sub c. So how many morphisms does this category have? I've added an equation that says that f semicolon f, or f composed with f, is identity. Yeah. Yeah, this category is the monoid z mod 2z. A monoid, mono means one, and a monoid, we talked about it another day, but you can also think of a monoid as a category with one object. So here's a category with one object, and when you think of the monoid as some set with operations, a set where you can add or multiply, the set we're talking about is all the paths. So if I have the path 3 and I have the path 2, 1, 2, I can compose them and get the path where I go around 5 times. And that's the monoid of natural numbers. In this one, I have the path stay at C, I have the path F, but then FF is just staying at C again. So it's kind of like the person, yeah, I don't know, you can say. The person, for some reason, if they turn around twice, they feel like really good, but if they turn around once, they feel like something's wrong. So this thing has 2 morphisms, once and no times. It's either happy and at rest or excluded. And this is a monoid. This monoid is sometimes called Z mod 2Z, or Z2. Any questions on this? Yep.
I'm not sure I get the idea of morphisms right. So for the free square, why isn't it an infinite number of paths because you have composition?
Right, so in the free square, these are just notation. It's the notation of a graph, and then that graph corresponds to a category. So how do you get a category from the graph? You take the dots as the objects, you take the paths as the morphisms. And then your question is, why are there not infinitely many paths? A path is a head-to-tail sequence of arrows. Start with it.
I thought it that way. I thought it was a never mind.
Oh, maybe you thought that one went backwards, or
Yeah.
that these went backwards? Oh, yeah. If those went that way and these went this way, that would make lots of, yeah, okay. Okay, other questions? Yeah.
Sorry. I'm having a hard time understanding why the composition of the identity multiple times doesn't accrue.
Doesn't
additional
accrue?
morphisms the way it
Because
does
in this, it says that when you do the identity with anything, including with the identity,
Yeah.
it's as though you just didn't do the identity. So this forces you, it's, right. It's composition is a function that takes something here, and gives you something there.
Yeah.
And that function is required to be such that identity does not accrue.
So
Okay.
in these presentations, morphisms are paths, and composition is concatenation of paths.
Sure.
But the identity is the path of length 0 on an object. So if you concatenate something with a path of length 0, you're adding nothing to it, so it remains the same. But even if you do that multiple times, it still remains the same.
And also the loop drawn in that N one, that's not the identity, that's like an extra.
Right, that loop there is a,
It's like
is a
a
jet.
If you want to
Yes.
use Hasse diagrams to indicate categories, then you have to make, then it's best, I mean, you have to choose some convention, and it's best to say, if I don't write it, I'm not going to indicate it. So, or if anything that's implicitly there, I don't have to draw. Okay, so what's another example? The category of sets. Set, the category of sets. So it's objects. I didn't write ob for each of those, I just told you in words. Ob of that one has 4, ob of that one is 1. Here, ob set is all the sets. Oh, did I? Oh, I always forget to do this. This is sometimes, this can be a large set. There's a distinction of small and large, or what's called a class. That's not a very important distinction. The only reason I have to say that is because someone would otherwise complain, is there really a set of all sets? And there's not, but there's a class of all sets. Or there's a set of all sets smaller than some cardinality. And so you fix what's called a Grothendieck universe. You fix a cardinality or a universe where all of your calculations will take place. And then you can talk about things like all sets that are smaller than, say, some inaccessible cardinal or something. So if you're worried about that, it's because you've been trained to be, probably more than because it's actually a worry. But that's my own bias. Okay, so the objects of sets are all the sets. If I have two sets, S1 and S2, then the set maps, so this is my C in that picture over there, C. Set maps from S1 to S2 is functions. So in the category of sets, the objects are sets and the morphisms are functions. And the identity on S is the usual identity. Usual identity. It sends every element of S to itself. And the composition is the usual composition. You can compose two functions. That first day I was like very concerned that maybe people didn't know how to compose functions, but I think hopefully you do, or you would have talked to me already. So, that's the category of sets. But there's also similarly the category of vector spaces. And I'm not expecting you to know what a vector space is, although many of you probably do. And here, the objects of vect. And you can replace vect in your mind with the category of groups, or the category of rings, or the category of topological spaces, if you know what any of those things are. But the objects of vect are all vector spaces. There's also a category of finite dimensional vector spaces. There's a category of vector spaces of dimension 17. The objects of the category of vector spaces of dimension 17 are all vector spaces of dimension 17. It's not a category theory a category anyone studied before. So if you want some new research, you can cast. Object of vect is all vector spaces. What are the vector space maps from V1 to V2? It's the linear transformations. F that are linear, that preserve sums and preserve scalar multiplication. The identity is usual identity, the composition is usual composition. Same with groups, same with posets. The category of posets has as objects all posets, or partial orders, or preorders, and as morphisms, all monotone maps. Okay, so, and finally, I said a database, so here's a database. that is also a category. The objects are the 3 dots. The morphisms are all the paths, except that I've considered 2 paths to be the same. Or if I start an employee and I see where they work in, and I see where the secretary works in, then that should be also equal to where the employee works in. All right. So it's all the paths in there where we mod out by this equation. Whenever you see anything dot secretary dot works in, you can erase that. Okay. So why don't you discuss with a neighbor what's happened so far in the class today, what all this was about, whether you understand it, what you didn't get, etc. Try to come up with something you don't understand between the 2 of you, or something that exchange information. So go ahead and do that.
I see, like, that's like an that's like that. I think like I kind of just say like fast and not like these yeah, a category that's like, yeah, I don't know anything like I'm not it's just a map like one of those it's like
What part of the body is not yeah,
yeah, I don't I would have done like
Okay. Start to wrap that up. Okay. Did anyone have any questions, or did anything come up for anyone? Yeah. On the second category, yeah. Okay, so someone asked a question. They were asking about the category of sets. So in the category of sets, they wondered whether there's a function from a set to the empty set. Is that the question? And the answer is that's part of the definition of function. So to answer that question, you would go back and remember what a function is. And you would ask, is there a function from a set to the empty set? And what it is for every element of this one, you need an element of that one. So if this is non-empty, you can't do it. But if this is empty, then there is one. So one way you could say that is it's called a strict initial object, which says that the only function into the empty set is an isomorphism. The only function into the empty set, or morphism into the empty set, is the identity on it. So the answer is rarely. There's rarely a function. Yeah?
Is there anything in the definition of a category that requires you to have these vector, like for functions?
No. No, you could take the category whose objects are vector spaces, but whose morphisms are all functions.
Yeah, but sorry. What I mean is, is the linear there necessary, or is it only useful because of?
It's the one everyone studies when they're studying linear algebra.
Yeah. Okay.
Yeah. So what I'm saying here in these examples are ones that categories we find often in mathematics. We don't find the 17-dimensional vector spaces category often. And we also don't find a category where that's not linear. Other questions? Yep.
In the definition of a category, I get that like a type of morphisms, but by itself, what exactly is a morphism? Like, what does it do?
Nothing. It's a placeholder that's expecting you to tell me what yours is. It's like, what is a name? Or what is? It's a name is expecting Bob or something, right? You're supposed to fill it in. So what is meant by morphism is up for you to decide. So what I often say is when someone specifies a category, they have to tell you a class of objects. They have to tell you for everything how to find the morphisms. Like for any two objects, you're allowed to say, what are the morphisms between these two? They have to tell you what the identity is, and they have to tell you what the composition formula is. So yeah, kind of a placeholder waiting for you to tell me what yours are. Other questions?
What's an example of a category studied in math where in the last axiom, the composition is not actually the composition?
Oh, where it's not actually the composition. Well, what's the composition of works in a secretary? Oh, you said in pure math.
Or in math in general.
Where the composition does not feel like composition.
No, it's like when it's not F composed G.
Well, it'll be written F composed G, but
I mean, in vector space, in the vector category or in the second category, it's like the composition in axiom 4 is literally the composition of functions. As
Right.
I know it.
right. But in this category that I just erased,
What's that?
if I have this category, I guess I didn't write it. Com squared. F, G, H, I, where F composed H equals G composed I. This is a category. It's got 4 objects and, I don't know, 7 morphisms or whatever, or 9 morphisms, because this one and this one are the same morphism. And you can read off the composition law just by thinking about it. And, but this is not a function. This is just a symbol. This category has 4 symbols as morphisms, or 7 symbols as morphisms. Nothing's being composed in any set theoretic sense. Now, does this ever occur in pure math? It does in category theory, because every time you see a commutative diagram, that you're actually talking about a functor. If someone says, "Oh, I have a commutative diagram of sets," they're going to give you 4 sets and 4 functions, and they're going to ask this to commute. And so they're actually just giving you a functor from this to here. So any diagram you see in a category theory paper is actually just a functor from a tiny little category like this into your category. So it's a useful idea, but does not use real composition, just the idea of composition. Yeah?
Adding on to that, I think pure mathematicians use posets, metric spaces, and fundamental groupoids, and none of which use like function composition for the composition.
Mm-hmm. Right, so let's say you're talking about the fundamental groupoid. You have some space. That's supposed to be like a hole in the space. And then you draw, then your objects are all the points of this space. There's 3 objects. And the morphisms are all the paths you can do. So that's a path, that's a path. Where 2 paths are considered equivalent if you can kind of, let's not worry about that. But, okay, so we have all these paths. And what he's saying is that when the composition is concatenating the paths. That's not composition of functions. So yeah, thanks. Other questions? Yes.
Are functors basically going from one category to another?
Yes.
So like data transformation?
Yes, they're going to be what we use for data transformations, or they're going to specify how the data should be transformed. And the data will have to transform somewhere through that functor. Right, so if vect is the category of vector spaces, it has vector spaces as objects and things that preserve those structures. What is a vector space? It's some stuff, some elements like vectors. It's so this is the last thing I was going to say today. Actually. So for each kind of category, there's the objects are kind of tuples of like some elements of some sort, or sorts. They have, so this is all just for intuition purposes only. Elements, structure, and stuff. Sorry, structure and properties. So in vector spaces, every object is a vector space, and it has elements, namely vectors. It has structure, namely the ability to add or scale vectors, and it has properties, like if I add two vectors, it's the same as adding them in reverse. In posets, the objects are partially ordered sets. They have elements, they have structure, the order, and they have properties, reflexivity and transitivity. So these are the objects, and the morphisms of the category, they send elements to elements, and they preserve structure. So this is all very kind of loosey-goosey, but we can kind of, I mean, I'm just kind of drawing some weird things on the board and saying stuff, but just imagine, what are the morphisms of vector spaces? They send the elements of one vector space, the vectors, to the elements of the other, and they preserve the structure. It's preserve plus. But the properties kind of disappear. You forget about the fact that the plus is commutative when you're looking at linear transformations, right? You stop thinking about them during the morphisms, right? When you're looking at a morphism, you forget, you don't care about the fact that they're commutative. That's more about the objects. Okay, so in the same way, if we wanted to come up with what cat should be, the category of categories, we've already said what its objects are. Its objects have a certain sort of element, namely it has objects and it has morphisms. It has certain structures like composition and identity, and it has properties like unitality and associativity. And so that should tell you or give you a good guess for what the morphisms between two categories should be. They should send the elements of one category to the elements of the other, so they should send objects to objects and morphisms to morphisms. They should preserve the structures. They should preserve identities and composition, and we're going to forget about unitality and associativity as we look at the morphisms. So the morphisms, so the objects are categories, and morphisms, cat C1 to C2, are called functors. And that's what Brendan will talk about on Tuesday. So, okay. Stay around for the fun time if you want to have categorical fun.